Good morning everybody. Today in these sessions I am going to speak on a subject called DSP where FFT algorithms will discuss. Here in these sessions we will discuss the derivations of first decimations FFT diagram. Right? Now by doing this, right, we can reduce, actually in these sessions we'll see, right, in the direct method, for example, if you want to convert 8-point sequences from time domain to frequency domain, you need 64 complex multiplications. If you use these derivations, or algorithm, FFT first decimation algorithms, this has been reduced to 40 complex multiplications. That means same sequence DFT converted into time domain to frequency domain with the cost of only 40 complex multiplications instead of 64. That means 24 complex multiplications we can save here by seeing this first decimations, by deriving this beautiful first decimations FFT algorithm or the flow diagrams. Right? This is my session number 3 and video number 3 of FFT chapter, which is coming under DSP under module 2. This is coming under VTU syllabus for 5th semester EC students specifically, and any other branch students, who are very interested in the signal processing. Now let me see, for example, this derivations of DIT FFT, how to derive this algorithm, beautiful algorithm, first decimations algorithm. Now I told you, here what we will do is, first step we write DFT of endpoint, any endpoint sequence x of n, as x of n is given by standard equations. X of k is equal to, this is known, 100 times we have written, summation n is equal to 0 to n minus 1, x of n, omega n to the power k in standard expressions. That means you can change time domain signal x of n into x of k by using the standard equations. This is endpoint DFT. Now, according to our divide and conquer approach, what we will do in these derivations, we will divide the endpoint sequence into 2n by 2, then take each n by 2, divide into 2n by 4, like that it goes. Now let us see how to divide endpoint into 2n by 2 point DFT. For example, this is endpoint. How to convert this into 2n by 2 point DFT, we will see now. Now immediately decompose the sum into two parts. One as even sample, other as odd number of samples, like this. For example, x of k is equal to summations, n is equal to even, let's say 0, 2, 4, even to n minus 2, x of n omega n k plus summations odd sequence, n is equal to 1, 3, 5, 7, n minus 1, odd, x of n into omega n power k. This is same. Omega x of n into omega n k is same. Now, this is second part. So immediately I told you, n point should be divided into n by 2. That means I want n by 2 point. Instead of n point, I want n by 2 here, n by 2 here. What I will do is, I will substitute n as 2r in the first summations, and I change summations into 0 to n by 2 minus 1, like 0 to n point. Here also same. 0 to n by 2 minus 1, right, like that, and here I will substitute n is equal to 2r plus 1. That's a math actually. Let me do that. For example, substitute n is equal to 2r into first summations. Here, n is equal to 2r plus 1 into second summations, so that we will get 2n by 2 point DFT. We'll see how do I get that. For example, here see x of k is equal to r is equal to 0 to n by 2 minus 1, new summations, n by 2 point summations, and sequence is variable is changed from n to r. Similarly, here also r is equal to 0 to n by 2 minus 1, x of 2r plus 1. Here x of 2r plus 1, here x of 2r. And here omega n to the power, what is n? N is nothing but 2r into k. Similarly, omega n to the power k into what is n? 2r plus 1. How to get these summations? R is equal to 0 to n by 2 minus 1, this I have shown. R is equal to 0 to n by 2 minus 1. Earlier, what is the summations? Earlier is Actually, this is the summation. N is equal to 0 lower limit, n is equal to n minus 2 upper limit. Now let me see, for example, how do I get this? N is equal to 0, what is n? N is 2r. 2r is equal to 0, r is equal to 0. Therefore, lower summation is, lower limit is r is equal to 0, here r is equal to 0. Upper limit is n is equal to n minus 2. What is n? N is 2r, 2r is equal to n minus 2, r is equal to n by 2 minus 1. See, this is the upper summations, right? Upper limit. See now, r is equal to 0 to n by 2 minus 1, x of 2r, omega into 2r, k. Even sequence over. Similarly, how to get this second even summations limits? That is shown here. For example, here see, this is r is equal to 0 to n by 2 minus 1. How do I get this? First see this, n is equal to 1 is lower limit, n minus 1 is upper limit. Now to get this, for example, go here. When n is equal to 1, what is n? N is equal to 2r plus 1, second term is equal to 0, 1. R is equal to 0. Lower limit is r is equal to 0. Upper limit, n is equal to n minus 1. What is n? 2r plus 1 is equal to n minus 1. R is equal to n by 2 minus 1. Upper limit is this. Now this is how I am getting, right, this limits. R is equal to 0 to n by 2 minus 1, x of 2r plus 1, omega equal to k into 2r plus 1. Now what is missing? Now I got n point is divided into 2n by 2. This is 1 n by 2, this is other n by 2. But what is missing? Here n by 2 is there, here omega n is there. Here n by 2 is there, omega n is there. Just bring this 2 down. So that this is n by 2, this is n by 2. Instead of omega n to the power 2rk, I will write omega n by 2 to the power rk. See that is what I do. N r is equal to 0, n by 2 minus 1, x of 2r. Omega, this 2 I bring it down. Omega n by 2 to the power rk, both are same. Similarly here, first split here. Here you split these two. Omega n to the power k 2r into omega n to the power k. That omega n to the power k term is very, very important. Take out this. That plays an important role here. Then rest you write. That's what I do. For example, omega n by 2 to the power rk. Now n by 2, n by 2. Omega n to the power k. That you write separately. Omega n to the power k you write separately. Rest you write separately. Now you get expressions as exactly 2n by 2 point DFTs. From n point to 2n by 2 point DFT. For example, r is equal to 0 to n by 2 minus 1. X of 2r. Omega n by 2 to the power rk. See now, this is n by 2. This is n by 2. Omega n power k, you take it outside. R is equal to 0 to n by 2 minus 1, x 2r plus 1, omega n by 2 power r. Now this whole term is written as g of k. This whole term is written as h of k. G of k is nothing but this is x of 2r is 1n by 2 point DFT. Omega 1 complex number. Omega n by 2 to the power rk is the other complex number. That means n by 2 into n by 2 square, like that. Right? Now that I will write like this. X of k is equal to g of k plus omega n k into h of k. This is k ranges between 0 to n by 2 minus 1. That means 0 to half. If you take 8 point DFT, right, half point you will get from this. What is that? x0, x1, x2, x3 is first half point. Then x4, x5, x6, x7 is the next half point. I want, right, this is half point DFT. N point is divided into 2n by 2. This one n by 2, the other n by 2. But other half point, n by 2 to n minus 1. That means 4, k is 0, 1, 2, 3 you will get here. K is 4, n by 2 is 8 by 2 is 4. 4, 5, 6, 7 I want from the half point to the end point. That's why what I write is g of k and h of k are even index samples and odd index samples. The required equations to get n point DFT complete can be written by these two forms. What is that? First is x of k is first line is as it is. This g of k plus omega n to the power k into h of k. Where k ranges between 0 to n by 2 minus 1 to n by 2 point DFTs. Now, after the end, k ranges between n by 2 to the n minus 1 is written by g of k. Just only one change is this n by 2 is there. For example, n is 8, 8 by 2 is 4. 4. That n by 2 right here, just add g of k plus n by 2 plus omega n to the power k into h of k plus n by 2. This n by 2 right. Now remember these two expressions. By looking these two expressions, we can write the flow diagram. You need not have to mark this diagram. By looking these two expressions only, we can write 0 to half point DFT and half point to end point DFT. Now let's see how to write this now. This flow diagram. For flow diagram for first stage decimation is given by, for example, let's say x of n is 10101010 sequence. X of k is equal to 4 0 0 0 4 0 0. Frequency samples I get. For example, this frequency samples, DFT outputs. This is input, time domain input. How do I write now? For example, I said the n point is divided 2n by 2. This one n by 2 DFT, the other n by 2 DFT. This is E1, this is R. Now inputs are, its inputs is like this. X0, X2, X4, X of n by 2, E1 inputs. Then time domain, odd inputs. X1, X3, X5, X of n minus 1. So this is odd inputs. N by 2 point DFT, N by 2 point DFT. Outputs are G0, G1, G2, G3. G of n by 2 minus 1. This is for the even samples. That is this. See this? This is for the even samples. Even samples. Right. G. This is called G, no? I told you, no? This is called G. G of H. G of K. Now, similarly, this is H. H0, H1, H2, H of n by 2 minus 1. Now, draw 8 lines, 1, 2, 3 straight lines. You will get outputs like this. X0, X1, X2, X3. Let's say 80 outputs. X3, X4, X5, X6, X7. Outputs are this one. 4, 0, 0, 4, 0, 0. Like this you will get now. Now, what's the difference between this algorithm and direct DFT? If it is direct, we are here also doing the, basically we are converting time domain into frequency domain only. Same output we are getting. But we are getting at the cost of 40 complex multiplication here instead of 64 in complex in direct method. Now let's see how it is. For example, draw 8 lines, draw the butterfly diagrams like this. First butterfly is written between G0 and H0 input. Second butterfly is written between G1 and H1, G2 and H2. Fourth butterfly, last butterfly is G n by 2 minus 1, H of n by 2 minus 1. For example, let me consider first butterfly. This G0 and H0. G0 and H0. Here omega n power 0 is there. Omega n power 1, omega n power 2, 3, 4, 5, 6, 7. If it is 8 point. Right, this is called n point combining algorithm. Now, let me take this first output, first butterfly. Inputs are G0 and H0. Output is X0 and X of n by 2. Now let's see. X0 and X of n by 2. Let's see how to get this. For example, X0 is equal to, see this now, K0. When K is 0, you will get X0. X0 is equal to G0 plus omega n power 0 into X0. That is what X0 output. See now, that's how we get. X0 is equal to G0 plus X0 into X0 along with multiplied as omega n power 0. We get X0. Similarly, X1 is nothing but G1 H1 into omega n power 1. See now. For example, K is 1. 0, 1, 2, 3. You will get. Half. N is 8 point mean first half you get 10. For example, 1. X1 is equal to G1 omega n1 H of 1. See now. That's how we get. X1 is equal to G1 input H1 into omega n power 1. Similarly, you get everything. For example, here half point. Let's say, right, this one. X of n by 2. The other leg. This X of n by 2 is nothing but first G0 H0 into omega n power 0 over no. X of n by 2 is the other leg of this butterfly, right? This butterfly. Here, the output X of n by 2 is nothing but, see now, here you have to come. For example, 4, when K is 4, X4 is equal to this equations now, 4, 5, 6 and all this. G, for example, X4 is equal to let's say when k is greater than 4, less than n minus 1. Here n by 2 is 4. 4 plus 0 is g4. Omega n power 4. H of k plus 4, 0 plus 4 should be g4. Therefore, you will get like this. g0, h0 into omega n by 2 to the power 4. This n by 2, whatever n is there, that is equal to this. Similarly, second one, this is this and this and this. Third one is this and this and this. Last one is this and this along with this. Is equal to, you will get these outputs. You will get at the cost of 40 complex multiplications. Let's see how. For example, this is what it benefits. First stage of decomposition, total number of complex multiplications eta one required to get NPDFT is, for example, eta 1 is equal to, let's see the application side by writing the diagram. N by 2 square plus n. This can be written as, how this is n by 2 square? This is for the even sample. N by 2 into n by 2 complex multiplications for even samples. That's the meaning. Let's see now. N by 2 into n by 2 complex multiplications for the odd samples. N is the combining algebra. That means, for example, let's see now how I am getting n by 2. See now, here see this, n part is divided into 2n by 2. This is one n by 2, this is other n by 2 into omega n power. For example, here this is even samples. Now see this n by 2 point DFT, this x of 2r is 1n by 2. Is 1n by 2. This x of n 2r. This, right? This omega n by 2 to the power rk is the other complex number. N by 2 point complex number. This is n by 2 complex number. Ready? Multiplications, repeated multiplications of 2n by 2. For example, n by 2 square. N by 2 into n by 2. N by 2 square you get from the even terms. That is what is n by 2 square. Right? Complex multiplications from even. Similarly, n by 2 square complex multiplications from the odd. From the odd. For example, see now. Here, this is one complex number of n by 2 point. This is another complex number of n by 2. N by 2 into n by 2. N by 2 square. See now. N by 2 square. For the odd. And plus n is common everywhere. See this? N is whatever the output. x0, x1, x2, x3, x4, xn. Each time you are multiplying this term. Omega n power 0. Omega n power 1, 2, 3, 4, 5, 6, 7. See now, irrespective of half point, 0 to half or half to full, you will always multiply this h of k with omega n power 0. Omega n power 0 to 3, 4 to 7. Therefore, this is n. N point is for combining algebra. Now, simplify this. Eta 1 is equal to total complex multiplication is equal to 2n by 2 whole square plus n. That is n square by 4. 4 is n square by 2 plus n. Therefore, if you take up an 8-point calculation example, then 8-point DFT from conversions of x of n to x of k, then 8 square by 2 plus 2, 8. That is 64 by 2, 32 plus 8, 40 complex multiplications. Earlier 64 complex multiplications is being reduced now to 40 complex multiplications if you use this FFT first decimation algorithm to get 8 frequency sample output, same output from the same input. Now that means you are saving, if you use this method, you are saving 24 complex multiplications. Assume this increases speed of your processor, and this is how it saves labor, it saves processor time. And today's applications is after all, right, 1000 times of conversions of this type of time domain to frequency domain equations. Right. Next class, right, let me do second decimations diagram. By doing that, even 40 complex multiplication is being reduced to 32 complex multiplications. Right. Wait for that video. Till then, right. Thank you very much for your patience listening. Right. Now your duty is to study this, subscribe this and send it to your friends, whoever interested in studies. Let us study together. Right, before ending this again sessions, let me again read out one beautiful quote. Right, this quote says this: before any success or successful personalities, right, always we should see the arguments, then oppositions, then only success we will get. Right, that means to get success, argument is must. Everyone, oppositions you have to face. Finally, you will get success. Right. By saying these few words, thank you very much.